Our third changemaker of the evening is Saloumeh Ghasemian. She is a PhD student in the Department of Chemical Engineering, working with Professor Sasha Omanovich in the Electrochemistry and Corrosion Laboratory. Saloumeh is going to tell us tonight about how we can use electricity to clean wastewater, to treat both the pharmaceutical drugs that we're flushing down our drains at an alarming rate, as well as to treat pathogenic microbes that can cause illness and death, as occurred in Walkerton, Ontario in May of 2000. And so Saloumeh will tell us how to use electricity to purify our water. Saloumeh.
Thank you. If you brushed your teeth this morning, or took a shower, or had a cup of coffee, consider yourself lucky. For us, water is taken for granted. Clean drinking water is always within reach. But as we all know, this is not the case for everyone. Large parts of our world survive with insufficient drinking water. As Sarayu told us already, 800 million people lack access to clean drinking water, and that is 1 in 9 people. Children cannot go to school because they have to work hours to get daily supply of water. And this is not the case only in underdeveloped countries. In a developed country like Canada, there are also some people facing bad water conditions. At any given day, over 1,000 boil water advisories are in place across the country. How much water are we using? An average Canadian uses 329 liters of water per day, or around 10,000 liters of water per month. That is enough water to fill 100 bathtubs. A study in 2009 showed that Canadians ranked second only to the United States in terms of highest water use in the developed world. And they use more than twice as much as Europeans. How about wastewater production? An average Canadian produces 668 liters of wastewater each day. Only in Montreal, the daily production of wastewater ranges from 2,500 million liters per day on dry days up to 7,600 million liters per day on rainy days. So each day, we produce enough wastewater to fill Olympic Stadium. And that water needs to be treated before it is returned to St. Lawrence River. So water treatment process plays a very important role in the water cycle. In Canada, one of the main reasons of contamination of water resources is mixing with untreated or improperly treated wastewater. This is what a conventional wastewater treatment process typically looks like. The screening and primary settling processes mainly remove floating and suspended solids and metal ions. Biological treatment uses microorganisms, primarily bacteria, to convert tough organic matter into simple substances and additional biomass. Then the produced biomass and waste are removed in the secondary clarifier. And the last step is usually disinfection. But keep in mind that wastewater treatment process has to get rid of a wide variety of contaminants dissolved and suspended from small microorganisms to larger particles. Conventional wastewater treatment methods are in certain cases ineffective or insufficient for the removal of biorefractory organic compounds. And that is when advanced treatment options come into play. Advanced oxidation processes, or AOPs, are chemical oxidation processes that involve in situ generation of highly reactive oxidizing agents, such as hydroxy radicals. AOPs were first proposed in 1980s for potable water treatment, but later they were broadly applied for the treatment of different types of wastewater. AOPs include several technologies, such as electrochemical technology, ozonation, and so on. And they have several applications for wastewater treatment, including the reduction in total organic concentration and specific pollutant destruction. Advanced oxidation processes are very efficient methods to increase degradability of those organic matter that are difficult to degrade by means of biological treatment as a pre-treatment step, or to remove those organic matter that are not treatable by biological processes at all as a post-treatment step. Among these AOPs, electrochemical methods have gained great attention in recent years for the treatment of wastewater containing organic compounds. In this image here, you see a typical electrochemical reactor for wastewater treatment, which includes an anode, a cathode, which are connected to a power source. Organic compounds are oxidized at the anode surface by losing electrons and are converted to CO2, water, and more simpler products. Anode here acts as a catalyst, and hence this process is also called electrocatalysis. The electrons then travel to the other side of the cell, where some cathodic reactions, such as hydrogen evolution, take place. This process has many advantages, such as versatility, environmental compatibility, no need to add auxiliary chemicals, no need to high temperature and pressure, so safe operating conditions, easy process automation, minimum solid waste production, and so on. If a light source is added to the system, the process is called photoelectrochemical oxidation or photoelectrocatalysis, at which the anode material plays an intermediate role in absorbing light energy and promoting desired reactions. Our focus in this work has been on the anode part and specifically anode material. Now that I talked about the theory, I move on to the experimental results. My experimental work started with preparation and screening of anode coatings composed of tin and tungsten oxide, doped with a small amount of antimony oxide. Anode coatings with 6 different compositions of tin and tungsten oxide, varying from 100% tungsten to 100% tin oxide, were formed on pre-treated titanium substrate by a thermal deposition method. Then each of these electrode coatings was tested in photoelectrochemical process for a degradation of a model organic molecule, which in our case was phenol red. As you can guess from its name, phenol red has red color. In the picture above, you see phenol red in the samples taken from the reactor at different times during the experiments, filled in the cuvettes. And as you can see, the phenol red was almost completely removed from the system after about 120 minutes. The results for the removal of phenol red by using 2 processes of electrocatalysis, which is the use of electricity, and photoelectrocatalysis, which is the use of UV and electricity at the same time, are shown as graph bars. And as you can see, the coating composition with 80% tin oxide and 20% tungsten oxide exhibited the highest degradation percentage for removal of phenol red. So this coating composition was selected as our best candidate for further experiments. But in order to proceed and design our experiments, we had to know what the major threats to water quality are. One of the major threats is contamination of water with pharmaceuticals, and another one is contamination with waterborne pathogens. First, I'm going to talk about the contamination with pharmaceuticals. Pharmaceuticals have been detected in concentrations up to 1 microgram per liter in a wide variety of water samples from sewage flows, lakes, rivers, groundwaters, and seawaters. Although the concentration of these compounds in water bodies are very low, their continuous input may pose potential hazard to living organisms. A study reported in Germany in 2015 showed that most drug residues in wastewater come from households rather than pharmaceuticals, rather than hospitals and nursing facilities. These pharmaceuticals can come from human excretion or disposal of expired drugs into sinks or toilets. We chose a pharmaceutical, carbamazepine, to test the effectiveness of our selected coating composition for the removal of a drug. Carbamazepine is a widely used anti-epileptic drug and is persistent to conventional wastewater treatment methods and even some other advanced treatment methods. Here are the results for degradation of carbamazepine using both UV and electricity. As expected, by increasing the applied current, we obtained higher degradation of carbamazepine. However, for all applied currents, above 90% removal was obtained after about 20 minutes. If we compare the results of the electrocatalysis process with photoelectrocatalysis process, we find out that at lower currents, photoelectrocatalysis process works much better for the removal of carbamazepine. But as you can see, at higher currents, both processes worked almost similarly. It indicates that UV energy plays a more important role at lower currents. Now that we have talked about the contamination of water with pharmaceuticals, I'm going to talk about the contamination of water with waterborne pathogens and related diseases. Most of you have probably heard of at least two of these, Salmonella and E. coli. Waterborne diseases such as diarrhea and gastrointestinal diseases caused by various bacteria, viruses, and protozoa have been the causes of many outbreaks in the world. For example, Canada's worst ever E. coli outbreak that took hold in May 2000 in Walkerton, Ontario, at which 7 people died and 2,500 people out of 5,000 population at the time fell sick. According to World Health Organization, each year 3.4 million people, mostly children, die from contaminated water. According to UNICEF, United Nations Children's Foundation, each day 4,000 children die from contaminated water. So by improving water quality, the global diseases can be reduced by approximately 4%. So this is a very important concern that has to be addressed. So we tested the effectiveness of our selected coating composition for the inactivation of a test microorganism, which was, in our case, non-pathogenic E. coli. When there was no current passing through the electrochemical cell, no change in the concentration of E. coli was observed after 60 minutes. When there was a small amount of current passing through the cell, there was a small decrease in concentration of E. coli after 60 minutes. By further increasing the current up to 0.5 amp, there was almost instantaneously complete inactivation of E. coli in about 30 seconds. And that's very fast. And the energy usage for this inactivation was about 30 milliwatt-hour per liter. How much is this energy? This is like you turn on a 30-watt lamp for 3.5 seconds, which is not that much. Does this method only work on non-pathogenic bacteria? No. We also tested this method for the inactivation of pathogenic E. coli and also a more resistant bacteria called E. faecalis. And in all cases, the system inactivated bacteria in a relatively short time. So this method works for most of the bacteria and pathogens. The results we just saw showed us that the electrochemistry-based technologies work effectively for the removal of harmful and persistent contaminants from water and wastewater, including organics such as dyes, pharmaceuticals, bacteria, and pathogens. And this is very promising in the context of water purification. I personally would like to contribute to a work that takes us to a better world in the future, with improved water quality that ensures the availability and sustainable management of water and sanitation for all, for this generation of citizens and the next. Thank you.
Thank you very much, Saloumeh. So our second change maker of the evening is Zhen Yin from the PhD student in the Department of Mechanical Engineering, working with Professor Francois Bartholat in the Laboratory for Advanced Materials and Bioinspiration. Nature creates extremely strong materials like teeth and bones and seashells out of the relatively weak raw ingredients that it has to work with. And so Jen's going to tell us how we can take inspiration from nature to use low value and low quality materials like recycled plastics and glass in order to make sustainable materials that have very strong engineering properties. Jen.
Thank you. Good evening, everyone. So, what kind of waste materials we are talking about here? We all know plastic waste. They are in every corner of our life. Plastic bags, plastic bottles. They are hard to degrade and hard to dispose without further pollution. Construction waste is another kind of wasted materials that has become a big problem in many fast developing countries. And also, right here, right now, in Montreal, near our campus. Recycled materials, you may be surprised that I also consider it as one of the wasted materials. Why? Because recycled materials usually have inferior properties to its original materials, as it will be too expensive to regain its original properties. So usually, they can only be used in low-value applications, like building a desk or building a table. If left untreated, considering the amount of wasted materials we produce every year, we may be buried by those wasted materials eventually. So what do we do with them? Honestly, our current efforts to deal with those wasted materials are not very efficient. Take plastic waste as an example. We try to use biodegradable plastics, but are they really degradable? They can be degraded to small pieces, but those small pieces can no longer further degrade. For construction waste, it's pretty much the same story. For recycled waste, recycled materials, as I mentioned, they can only be used in low-value applications for their inferior properties. It is interesting that we always view them as useless materials. But what if we can view them from another perspective? What if we can turn those wasted materials into materials that are being useful in high-value applications? It would be great to do so, but the question is how we do that. I think I can give some few hints here. We can start thinking from the features of those wasted materials. For plastic waste, they're usually very ductile, but they are low on strength and stiffness. For construction waste, usually they are ceramics, bricks, or rubbles. They are relatively stiff and strong, but they are low on toughness, which means they are very brittle. And so ductile, but weak. Stiff, but brittle. Neither of those features are great for engineering applications. So who can make great materials from ingredients that have such features? Nature does. Many biological materials are super tough bioceramics that can be made of weak constituents, such as weak proteins and very brittle minerals, which were used to make chalks, and you know how fragile they are. Those biological ceramics achieve a toughness 3,000 times higher than its weak ingredients. And to keep it in mind, those ingredients are actually even weaker than the wasted materials I just mentioned. Another thing interesting to mention is that when biological systems create those materials, there's no pollution and low energy cost. As biological systems just recycle everything they need from other animals or from nature itself. Nothing would be wasted in our Mother Nature. Not only biological materials amplify the toughness, they also have balanced material properties which are usually mutually exclusive in traditional engineering materials, like stiffness and toughness. If we can learn from those biological materials, we may design new novel bioinspired materials that can be also made of weak constituents and has high performance. But first of all, we need to know how biological materials works. To understand how biological material works, we need to first zoom in. In the microscope, and unlike most of the engineering materials, biological materials has complex yet highly controlled microarchitectures. Each biological materials may have its own way of those architectures, but they do share some common features. Take seashells as an example. Usually, they are made of stiff yet brittle mineral tablets, and organic interface, which is ductile as the adhesive. So from this, we know that we can, this is more or less like linear and brick mortars, like what we do in the traditional architectures. So the next step, I would like to introduce the concept of architectural materials. As we all know, biological materials are kind of architectural materials. Architectural materials is a kind of material made of 2 or more ingredients with dissimilar properties. And for example, if we have a very stiff material and another material which is very ductile. So neither of them are great for engineering applications because they don't have very balanced properties and low toughness. Traditionally, we can laminate them, which is the working model and the loose model. But still, they are either stiff or very ductile. So for architectural materials, we combine those 2 materials into a sophisticated but well-controlled architectures. Therefore, we have balanced properties between stiffness, strength, and ductility. Therefore, we have a well-amplified toughness, which is energy dissipation. So biological materials is actually a very successful materials through billions of years of evolution. It provides great templates for us to design new bio-inspired architectural materials. But it will be not enough to just copy everything from nature because they use different kind of materials that we are dealing with. So we need to understand the mechanism behind those architectures. So I think we can conclude 2 basic guidelines from those biological materials. First, we need to exploit the full potential of each ingredient in these architectures. Second, by using those architectures, we need to let more and more contents of materials to get involved in the energy dissipation procedure. And all those ingredients should work together. Using nacre, which is the inner layer of abalone shell, as an example. Nacre is one of the toughest biological materials in the world. Usually, the brittle and stiff mineral tablets, they prevent strength and bridging the crack from its further propagation. And the sliding between the tablets also makes sure that all the organic interface are deformed in shear, which is their favorable way of deform. The interlocking between the tablets also makes sure that more and more volume of the materials will be involved in the deformation process, which means amplified energy absorption. And the shear deformation of those organic interface also relax the stress within the tablet and thus prevent it from breaking. And the weak interfaces also create a pathway for the crack to deflect, which prevents the catastrophic failure of the material. So by understanding also the mechanisms, we know that all those mechanisms contribute to the amplified toughness and balanced properties of the materials. But how can we implement them into the design of our new materials? I think our research proved the concept that we can indeed using bioinspiration and the concept of architectural materials to turn inferior materials into high value and superior materials. For traditional engineering materials, indeed, they are high in mechanical performance. But in the meantime, when we manufacture them, they produce a lot of energy consumption. And for recycled materials and wasted materials, we don't need any energy to create them. They are already there. But the problem is they have inferior properties because most of the time we just mix them together, so they don't have good properties. And thus, they can only be used in building a desk or building a tables. And we have to build that table very thick because they have inferior properties. Using the concept of bioinspiration, we can create architectures within those inferior materials. Therefore, we have an enhanced version of them, and we can have materials has as good performance as those traditional engineering materials, or even better. And in the meantime, we keep the energy cost low. Our current research are at a stage that we prove the concept that indeed we're using bioinspiration and the concept of architectures will create superior materials. And those materials we are using have similar properties than what the materials we find in the wasted materials. But still, we are using materials that are coming from standard factory. So it will be slightly different from what we can find from the wasted materials. So our next stage will be directly using the materials from wasted materials or using the recycled materials to try to create some materials that also have superior properties. And it will be difficult, as the materials we find in the wasted materials will be random, and it will pose difficulties for us to actually fabricate them. Our final goal is to actually build architecture materials which is high performance and low energy cost, and ready for high-value applications to build our world. And I think eventually we can build our world just like what nature does for billions of years. Nothing will be wasted in the future. Thank you.
Thank you, Zhen. So we have time as well for a few questions for Zhen. Everyone's too shy. Lauren, please.
So this composite material that you developed, is there a particular application for that you think that it could be for something?
Yeah. Actually, when we do it for the applications, we sometimes for the building materials and also for some protection systems, like for body armor, and we also do for laminated glass, which is for windshield or for the glass curtain wall, something like that, which requires toughness and impact resistance. Yeah, that's the application we are aiming for. Yeah.
Can it protect our iPhone screens from getting cracked?
Yeah. Yeah.
Great. Any other questions for Zhen? Please,
Hi.
there.
Would you be able to recycle these new materials?
Yes, for sure, because like I mentioned, those wasted materials are pretty random. It's coming from everywhere. And if you use up, for example, there's new materials, they're broken or something, and you put it in the garbage bin, it will be still the same way because we didn't change anything from its previous recycled or wasted materials. So we can still recycle them. That's for sure, actually. Yeah.
A last question? Thank you, Zhen.
Oh, thank you.
So it's now my pleasure to introduce our first changemaker of the evening, Sarayu Rao. And Sarayu is a PhD student in the Department of Civil Engineering, working with Professor Subhashis Ghoshal in the Benedek Environmental Engineering Laboratories. Sarayu is going to tell us tonight about how nanomaterials can improve technologies for sustainability, but how they can also have adverse effects on our environment and ecosystems. And she's going to tell us about her research in order to improve measurement techniques for nanomaterials in the environment so that we can assess their fate, their potential impacts, and design improved materials that can lead to more sustainable technologies. So Sarayu, please.
Thanks. I would like to describe a field in which little has been done, but in which an enormous amount can be done in principle. What I want to talk about is the problem of manipulating and controlling things on a small scale. There's plenty of room at the bottom. This was a very famous lecture by Richard Feynman in the year 1959, where the concept of nanotechnology was first conceived. What you see here is a 4th century artifact, the Lycurgus cup. What is so special about this cup? This cup is green and opaque under reflected light, red and transparent under transmitted light. What is this ancient sorcery? When this cup was being made, it was accidentally contaminated with minute silver and gold dust particles. These dust particles happen to be what we use to such a large extent today in our products and applications called nanoparticles. If you had to imagine one nanoparticle that was 1 nanometer big, take a strand of your hair, divide it 80,000 times, and that will give you 1 nanometer. Due to their extremely small size, nanomaterials are being incorporated into many products and applications. How many of us go through our day using sunscreens, cosmetics, toothpastes, electronic items? All of us, right? That's what I thought. Silver nanoparticles, for example, are used for their antimicrobial properties in many products. They're used in food packaging, in clothes, in medical dressings, and even in washing machines. This is just one example. Nanomaterials are also used in a wide variety of environmental applications like oil spill cleanups, environmental remediation, and even water treatment. Due to this, the global market for nanotechnology is now booming. In 2009, the global market was $254 billion. In just less than 4 years from now, the market is predicted to reach $3 trillion. That's approximately 12 times an increase in just about 10 years. Predictions and trends for growth and expansion are constantly going to be made. Having said that, we are the future generation, and our generation is probably going to be most affected by this technology for the better or for worse. So let's look at one such prediction that was done in 2010. What you see on your left are the top recognized nanoparticles that have been incorporated into consumer products and applications. And on your right, you see the different sinks where nanoparticles could eventually end up. As you can see from this figure, about 80% of nanoparticles end up in landfills. A small but significant amount do end up in soil and water systems as well. Upon entering the environment, these nanoparticles are bound to have interactions with organisms. It is very important for us to study these nanomaterial biological interactions so that we're able to determine their exposure and toxicity. There has been evidence that nanoparticles have been found to have ill effects on certain microorganisms and organisms. What you see here is the gills of a rainbow trout. And you can see with exposure and with no exposure, there's such a big difference. With an exposure of 500 micrograms per liter of titanium dioxide nanoparticles, the gills had a mucus lining membrane damage and edema. In another study, where they looked at the effect of nanomaterials in biosolids on the effect of plant growth, they found that these nanomaterials caused a change in the soil microorganisms, and due to this, the plants had stunted growth. The point I'm trying to make here is that nanomaterials have a wide variety of applications that make a better world. but at the same time, they're not 100% safe, and they are causing ill effects, as shown in these studies. Nanotechnology has the potential to provide us with cost-effective and efficient solutions for sustainable infrastructure, clean drinking water, and food safety. For example, nanoscale manufacturing can provide us with means for sustainable development where we use lesser materials, lesser energy, lesser water, and produce lesser wastes. All these applications are very important for a sustainable nano future. But I'd like to stop here and ask a question. What happens to these nanomaterials once the products are done being used? Let's all think about this together for a second. For example, we have our cosmetics, toothpastes that eventually get washed out and go into our sinks and then the wastewater treatment plant. When we're talking about bigger products like electronic items and food packaging, these end up in landfills. All of these are eventually ending up in one environmental compartment or the other. This is where my research comes in. We are trying to find the fate and behavior of these released nanoparticles from these products and applications. In order to do so, we have to develop techniques that can characterize these nanoparticles at low concentrations or environmentally relevant concentrations. Why do I pause here? It's because there have been studies on toxicity and fate of nanomaterials done at higher concentrations. But are these studies relevant? Is that what we're exactly going to see in the environment? Through my research, we really hope to look at the fate and behavior of these nanomaterials at low environmentally relevant concentrations. This, in turn, is going to determine if we need to design for more stability, if we need to change the way we're designing these nanomaterials, if we have to incorporate fewer nanomaterials in our products so that there's lesser release at the end. And all these together is going to affect the applications and their use in sustainability. I am now going to go into more details of my research and tell you how I'm trying to find the missing link for a sustainable nano future. What you see here is a model aquatic environment, and the small black dots are the engineered nanoparticles. They can go through a wide variety of processes. For example, they can come up together and homoaggregate. Some metallic nanoparticles can dissolve. Some of them can undergo surface transformation under the prevailing aquatic chemistries. And some nanomaterials can interact with colloids and bacteria and heteroaggregate. Each of these processes are very important to study because they are all going to ultimately tell us the fate and bioavailability of these nanomaterials. Or in other words, we are going to find out how available these nanomaterials are upon release for uptake by microorganisms and other bigger organisms. Now let's look at a more realistic situation. Imagine going to a river or a lake with a glass, getting a glass of water. What do you expect to find in it? There might be algae, there might be colloids, clay particles, bacteria, dead leaves, and maybe some nanoparticles. How am I going to pick out these nanoparticles, characterize them, and know their fate? It's like I'm trying to look for the needle in the haystack. And not only am I trying to look for the needle in the haystack, I'm trying to find its mass and size. And that's exactly what I'm trying to do through my research, find the mass and size of the needle in the haystack. Or in other words, try and find methods to characterize and quantify these nanomaterials once they're released. In order to do that, the first step was to identify nanomaterials we could work with. So we chose titanium dioxide and silver nanoparticles, which are used quite commonly in personal care products. We then used existing novel techniques and optimize them to measure these at environmentally relevant concentrations. So these are the different techniques that we have used through our studies. Dynamic light scattering and nano-tracking analysis are two light scattering techniques that give us information about the particle size. Field flow fractionation is a technique that is able to separate your particles according to size and give you information about their size distribution and their average size. And single particle inductively coupled plasma mass spectrometer, or SP-ICP-MS, is a technique for metallic nanoparticles that can give us information about their size, the dissolved concentration, the number of nanoparticles present, and the particle size distribution. Each of these techniques are able to give us information about size. What they differ in is the concentration that is needed for detection. And as you can see, as we're going lower, we're reducing the detection limit. When I talk about light scattering of nanoparticles seen under light scattering, it may be hard for you to imagine what it looks like. So here is a short clip of how nanoparticles behave under laser light. They are undergoing a rapid motion called Brownian motion. Smaller the particles, more rapid the motion. To your right, you see field flow fractionation. This is a channel where particles are being separated according to size using a parabolic flow as well as a cross flow. So the first step was to optimize field flow fractionation to detect nanoparticles. So we use titanium dioxide nanoparticles here. What I really like about field flow fractionation is that it gives you the entire composition of your sample. You see everything that there is. The peak here gives you the average size, and the little red dots gives you the particle size distribution. The next step was to work with slightly more complex samples. So for this, we used 3 sizes of silver nanoparticles. We first ran them in SP-ICP-MS, where we got a very nice size distribution. You may wonder what is wrong with this graph. It's representing all 3 sizes. But what we're not able to see is the exact composition of each of these sizes. And imagine going back to that reverse sample where you're trying to detect what nanoparticles are present and what compositions they're present in. This method lags behind. So what we next did was use these 3 nanoparticles to separate them using field flow fractionation. And here we have 3 distinct peaks of 10, 30, and 100 nanometers. Now going back to answering the river water question. It's great. So now if we were able to find a method where we're able to first separate our particles according to size and then analyze them for composition and concentration, we would be able to get much more information. And that's exactly what we did. We collected the samples after analysis on field flow fractionation and ran them on SP-ICP-MS. So first, we got the 10 nanometer particles, followed by the 30, and then the 100. We have now improved detection limits. We are able to go down to lower concentrations. We're getting information about particle size distributions. We're able to separate particles by fractions, and we're getting information about their size. We are now one step closer to measuring that real water sample. Sometimes when I get really involved in my experiments, in trying to get all my results, trying to get that perfect graph, more often than not, I forget what I'm ultimately trying to achieve. I forget the big picture. I then zoom out of the zone, and I think about how what I'm doing is going to make a difference in the world. There are currently 800 million people who don't have access to clean drinking water. That's 1 in 9 who don't have access to clean drinking water. 1/3 of the schools globally don't have potable water either. So you can imagine that's 1/3 of the children that don't have access to clean drinking water. This is an example of how nanotechnology is providing us a solution to such a big problem. Here, They used iron nanoparticles and silver nanoparticles, embedded them in membranes to purify water to make it free from arsenic and microbes. It's a great solution and a very inexpensive solution for 7 cents for 100 liters. As engineers, we're constantly creating products and processes to make the world a better place. As engineers, more so as human beings, we have to ensure we do this in a responsible fashion. If the science of the small and technology is actually providing us with solution for such a big problem like clean drinking water, we need to make sure it is done in a safe way. We need to make sure that it has no ill effects on human health or the environment. We need to do it for the world that believes in us. We need to do it for the people who believe in us. We need to do it for those children who believe in us. Thank you.
Thank you, Sarayu. So we have time for a few questions. If you'd like to go up to the mics on the side of the room, you're welcome to. If not, you can stand up and Sarayu would be happy to take a question. No? Yes, Heather.
To look at the particles and differentiate between those that might have coagulated with creatures like bacteria, or maybe coagulated with soil particles or humus or something like that?
That's a great question. That's exactly what my research is about. So we're trying to develop a technique where we're able to use field flow fractionation to differentiate between each of these fractions. So if we're able to optimize getting different fractions, so imagine like we're able to separate the small nanoparticles first, followed by the ones that have maybe coagulated or are attached to something else, and then analyze these fractions using single particle ICP-MS. We would actually know a lot more. We would be able to tell how much of it is aggregating. Are major particles that are present actually aggregating, settling down? Are they dissolving? I think we would get like a lot more information.
Any other questions? If not, let's thank Sarayu again for her presentation.